I want to say, so first I want to say thank you very much for giving me the chance to talk here. I hope that by the end, hopefully we can, I can show you something. So I've been doing my work at the University of Guelph with Alex Gezerlis as my supervisor, and we've been studying machine learning techniques for studying the finite size effects that occur in strongly interacting fermions, and we're specifically interested in neutron matter. So I'll talk about an overview of what we're going to, or sort of why we're studying this system, why we care about it, and why we're trying to carry out this investigation. So in very generally speaking, when we're trying to study matter, we have many different types of descriptions for them and different algorithms or models that we can come up with. But in general, they all have limitations, especially at the sort of particle level when we're investigating those scales. One of the, or at least in our context, the difficulty here is the limitation in particle number. So our simulations are typically restricted to finite numbers, and we want to describe macroscopic scales. So we're looking for a technique to try to improve our ability to do that. Machine learning techniques have been applied in huge areas all across the world. It's coming into our everyday life, and we're seeing it emerge in nuclear physics as a promising tool to solve different problems, to perform interpolations, extrapolations, and do things like modeling wave functions to try to capture the underlying physics a lot better. These algorithms are particularly useful because of their ability to extract those underlying dependencies, which hopefully allow us to extrapolate. We're going to be looking at some of the issues that we've run into in studying nuclear physics and associated with these finite size effects, these small data sets, since we're restricted in general by the computational cost. And to do that, we're going to be looking at two related systems, the unitary gas and the effective mass in strongly interacting neutron matter. These systems are related, and we can gain a lot of insight from studying them, and we'll see how we can perform these extrapolations in those cases. The approach that we're going to take is, in both cases, is going to be to look at the data set and how we construct it and fixing the data set. We'll find that there are features of the data that we might not think about that end up causing spurious effects that we don't want, and how we can identify them and develop metrics to, well, identify them. When we've resolved all of those sort of nuances, at that point, we can perform an optimization procedure and optimize our machine learning model to then perform predictions, which hopefully can generalize as long as we've done a good job and captured those underlying details. So that's what we're going to be doing. I'll start by talking about the two methods that are the most prominent in our work. So that's going to be quantum Monte Carlo, which is an integration technique, a stochastic integration technique that is aimed at solving the many-body problem by essentially solving Schrodinger's equation for potentials that can be very sophisticated. And in our work, we use the Argon potential and the Urbana potential, which are both quite sophisticated. And quantum Monte Carlo allows us to get variational upper bounds on that energy. So it's useful in that sense, and it provides us the ability to solve these high dimensional integrals or deal in this high dimensional space where standard techniques kind of fail. But one of the downsides to this is that it's very expensive. There's a cubic time complexity as the number of particles increases. So very quickly, at around about 100 or so particles, we run into an inability to compute them in a feasible time, so to run those simulations. To account for that, we make use of periodic boundary conditions. So the periodic boundary conditions you can see in this plot here, it's depicted as a box that's being tessellated sort of in 2D, but theoretically, well, in practice, it would be in 3D, but just for the visualization. And you can see that it is a reasonable approximation to the much larger system, at least visually. And there's obviously a lot more work that can justify that. But that's sort of one of the techniques that are used to resolve that. One of the consequences of this is if we look at the dependence of, or as the energy, for example, if we look at the trend for the energy as a function of the number of particles, we find that there is some limiting value in the thermodynamic limit or the macroscopic scale that we want to reach. And as we do our simulations, they might be higher, they might be lower, but in general, they tend towards getting rid of the deviation as the particle numbers rise. But occasionally, we'll find that there are some values that perform really well, like you see in this green region near n equals 66. Bulk properties like the system energy, the particle numbers tend to agree with, I'm actually going to skip that, sorry. So let me just try to reiterate that, I apologize. We're looking here at the finite size effects, and what I'm trying to say, sorry, is that there are particular particle numbers that in general, people tend to study. N equals 66 is a common particle number choice, and this, however, only applies for bulk properties like the system energy. For quantities that we're going to be looking at, things like the effective mass, which is a single particle description, that scheme no longer works. So we're looking to try to update it to kind of generalize that. To do this, we're going to be looking at our machine learning models to take in a data set and try to analyze those predictions and be able to extrapolate to those higher particle numbers. When we're doing these machine learning techniques, we're generally feeding in these data sets into these models and trying to tune the internal parameters of them so that they best match the data set. However, the data is extremely important that we put in. We want it to be representative of the so-called data generating distribution, in the sense that if we're trying to study some sort of physics, we need the data set to be representative of it. If there are certain regions where we're missing points, if there are certain regions that have a very large error, for example, it's going to skew our model's ability to learn that underlying relationship. So we'll take care of that. We also think about the different types of models and approaches that we can use, and there are many different machine learning models, things like classification, which has been used in studying the phase transitions of matter, regression, which is what we're going to be carrying out, and then things like ranking are machine learning techniques that are common in things like search engines, things like that. And at the end of the day, our ultimate goal of our model is to be able to predict not only the old existing data, but also the new data in an ability to generalize. So not just the data set, not just being able to reproduce the data set, but also generalizing to new samples. So that's sort of the overview of the machine learning and the quantum Monte Carlo, how they play together. And now we can kind of see how we'll study that in the case of the unitary gas. So I'll take a second. So for the unitary gas, we are working with a dilute and strongly interacting Fermi gas that acts as a good model for neutron matter in the limit of zero effective range. So from this data set, which is, we can ignore the lines for now, I'll mention them in a moment, but just these data points here, we notice the two dependencies here. So the unitary gas has quite a lot of simplifications that allow it to be parametrized by only two parameters, the effective range of the interaction and the number of particles in our simulation. And from that, we predict an energy. Looking here, we see that the effective range dependence is strongly linear. But the end dependence is very complex. And if we consider that, this is quite beneficial to us because it means that we can perform linear interpolations without loss of generality or without imposing any physics. However, if we try to do something like that for the end dependence, it would be very difficult. And so we look for using this to augment our data set by applying these linear interpolations and then extracting the values off that to build our data set. So that allows us to augment or to increase the size of our data set very easily, very cheaply, which provides a lot, which makes the learning process much easier for those algorithms. You'll notice that there are different colors of lines, and the reason for that is because these linear interpolations are nice, but we can consider them in different ways. We can think of fitting a line through each n, we can think of fitting a line of best fit through each n, We can also think of fitting a line of best fit that works through the whole data set. And we can maybe think of averaging both contributions. So if we look at all of those different slopes, we notice that in general, all three lines agree in all the locations except for n equals 70 and n equals 80. These different interpolations are designed to investigate sort of the local effects. So what's happening locally in the data set versus the overall. And the fact that we have this significant change is implying that these points are outliers. These occur at the high end, which we're really interested in. Our data set is small, and so this is very valuable, and we can't just arbitrarily throw it away. And so what we're looking for is to systematically study the effect of those outliers to figure out how it's going to affect our data set. In our preliminary work, we found that all of our predictions, regardless of, so we constructed 3 data sets, one from each of those slopes. We would pull points off of those slopes in order to generate a data set, which gives us 3 data sets. All 3 of them predicted the same trend. So there's a bit of detail here. We'll just look at the fact that the green, red, and black lines all match, or like all of these lines are on top of each other. And that sounds like a good thing because it means that the outliers weren't causing a problem because all the models agree regardless of how we fit it. Except that's kind of odd because we should expect there to be a difference because that's pretty significant. So to investigate what's going on, we looked at introducing what's coined the dataset balance parameter. What we're doing here is we're looking at the distribution here, and we see that there are lots of points at low n, not too many at high n, and so we notice that there's a much higher emphasis on the data set at low n. So what we do is we linearly interpolate the counts at each n to vary between the original distribution, which favors low n, to going to a uniform distribution, which favors all of them, and then a reflected distribution, which favors the high n. And as we're varying this, we're looking at the predictions that the networks make based on what fit they were trained on. In the leftmost plot here, the original data set has all of the predictions converge to the same value. That is the reason why all of those previous predictions were lined up on top of each other. If we put more emphasis on the higher n, we see that the predictions tend to diverge quite strongly. And so this is an important realization that something is not being learned by the networks. If we remove an arbitrary pair to see what the effect of removing pairs is, we see very little effect, which implies that the act of removing a pair doesn't do much. But if we specifically remove those outliers at n equals 70 and n equals 80, they all converge across the whole domain. And this is a really important property of independence, that it doesn't matter, and it shows that we're learning the underlying dependence regardless of sort of where we're looking, if that makes sense, at least within a much smaller error band. Having identified that, we can justify the removal of the outliers. We can consider things like statistical imputation, or I guess that's it. Yeah, but in general, it's going to be better to try to not impose it. And the model seems to do pretty well, even though there are, even because of that. To continue on, now that we've identified the data set and solidified it, we perform a hyperparameter optimization, which looks at all the possible, a subset of possible parameters of our actual model. So for our model, we're using feed-forward neural networks, which have potentially multiple layers. They have different sizes, number of nodes, number of parameters. They can be organized. And so we can kind of consider all of these as hyperparameter optimizations. Some of these we heuristically fit, like using, in this work, a single hidden layer neural network, but other ones we did this systematic investigation, and the regions here where it's lighter guide us towards the optimal values for that model. Once we have this optimized model that is able to generalize quite well, we then look at making our predictions, except that there's one slight detail, and that's that the data set size has a confounding effect. As we siphon off more points from those slopes, the testing and training data set become more closely related. So we look at plotting different sizes of the data set to find signs of fitting, of poor fit. We find with a very low or a relatively low data set size, f equals 1000, the peak at the low end is not captured. Conversely, there's a kink at around 1 equals 40, which is more prominent with n equals 5000. And so we're justified to take f equals 2000 as which represents the data set size, as the correct hyperparameter that best captures those details. And from there, we can take the networks and extrapolate to high n and use that as our estimate. So that's that approach. Now we can kind of see, maybe give a second to process, and then we'll talk about the effective mass. That'll be relatively quick. So the effective mass here is aiming to capture many-body physics and can be applied in things like energy density functionals, and can be related to observables like the maximum mass of the star, the heat capacity, and different sort of and different observables. So there's a good insight that we can gain about these systems by studying it. And in order to get the effective mass, or to define it, we are studying the dispersion relation of a particle in a system that's otherwise in its ground state. So we look at the difference, or we're comparing this difference between this ground state, which in this case has n equals 3 particles, and we're looking at the momentum of this excited particle that we add in. And we're studying sort of the difference there, because we just want to extract that single quasi-particle effect. And so what we can do is we can simulate these systems in quantum Monte Carlo to get an energy. We can fit them to extract an effective mass. And because they're linear, the slope is enough to get an effective mass. So we take the energy and momentum, fit them, and that's how we get our mass. The machine learning problem here is to try to extrapolate this and have our energies, which are interacting quantities and difficult to evaluate, be extrapolated to large n. For the momentum, it's an analytic quantity, and arbitrarily large, we can calculate it. However, when we take the natural approach and fit the energy onto the momentum, we result in these discontinuities that are odd, I guess. One of the reasons that we're doing this is if we look at the predictions for the energy in the top panel and the momentum in the bottom panel, the predictions that the networks are making are smoothing them. There's a smoothing bias inherent to the neural network that makes it difficult to capture these discontinuous effects. So when we were doing so we've had this fitting problem of fitting a continuous quantity to a discontinuous quantity. The remedy here is to simultaneously train on the momentum, even though it's an analytic quantity, so that both data or both terms have the same biases, and that when we do the fit, they actually end up effectively canceling. And so the contrast is quite significant between the analytic momentum and the predicted momentum. There's still a few caveats here. This is just a sample that certain features are captured, certain ones are not. And that in general, as they get to larger n, we still have some difficulties here. One of the things that we notice about the effective mass is that it's relatively constant. And one of the difficulties that we have in optimizing our networks is that there are so many parameters. Now we have 2 sets of networks. So we need a metric to try to put those two networks together and find the pair of them that is optimal, which is a little bit of an odder machine learning problem. So to do that, we select our optimal networks by noting that the variance across the domain should be very low for these network predictions as per the data set. Based on that, we plot this disagreement factor, which is measuring that variability for multiple different hyperparameters, and we take the ones that are the most similar, that capture the most similar features, as the best networks to use. This allows us to carry out predictions, and we investigate things like single hidden layers or multiple hidden layers, and also the domain that we use. But we take an average of this domain, and we're able to predict these energies. And there are some details here that are interesting to note, but I think I've run out of time. So I'll just end by summarizing and saying that we've trained neural networks on two related nuclear systems, the unitary gas and the effective mass. We've identified many data set issues, and we've shown how we can resolve them to improve our prediction quality. So hopefully you learned something, and if there are any questions, that would be great.
Great, thank you very much, Nawar. That sounds really cutting edge stuff. Are there any questions out there? Just to get the ball rolling, these sort of singularities, that they're not like magic shell numbers or something like that, are they? Or
are you referring to the discontinuities here?
Yeah, the discontinuities. Yeah.
So these are occurring from the shells specifically. So we're dealing with a system of fermions. They build in degenerate energy levels, and every time we move from one degenerate energy level as they fill in to the next one, we experience a jump. There's, yeah, you can work out the equations and see it as well, but yeah. Yeah.
And so you basically want on your neural net, you want to kind of have it nothing varying too quickly from node to node.
So the way that I would probably say it is that ideally we want the network to capture those kinks, but I guess you might say that it's a much more difficult problem, and the networks have an inherent bias that make it difficult. But you can remedy this very easily by doing that. So an alternate approach, something that you might want to contrast with, I guess, now that I'm just thinking, would be to try much harder to get the networks to train them to capture those kinks. It's definitely possible, but the networks struggle with it. So it just means that you'd have to take a lot more care to get them. But the physics is still conserved regardless. Yeah.
I'll keep going unless there's more questions coming in. So what's the sort of, how big is your network in comparison to the physical system? Like what's the...
Like, are you saying data points versus like how many data points, for example?
Yes.
So in both data sets, there are, sorry, in the unitary gas, there is about 137-ish total data points, but then we can interpolate, and that's what that F was. So we can increase the data set size by taking those interpolations to increase it. So in this case, we're dealing with about 2,000 data points. Our networks are single hidden layers, and when we perform our optimization, we find that about 50 hidden layers is sufficient to capture it. If we go higher, the performance kind of saturates and we don't gain much improvement from that. In the other case of the effective mass, there are, I think, closer to, I'd have to think, so 10 times, I think about 100 points as well, like on that order, yeah. I'd have to recheck that, but it's on that order, yeah.
And a bit of a dumb question. So you were comparing the ground state with one excitation. Are those the right things to compare, or should you have taken one of the particles out of the ground state to put it into the excited state?
I see. So you're saying take the 3 particles and then just excite one of them? Yeah.
Or maybe somehow if you're doing this in the grand canonical, or
my understanding would be that you could do this, but the effective mass that you would be describing, or the property that you're describing, would probably be a different quantity, I think. But Yeah, I think it's a slightly different quantity, but there are many different, and there are many different formulations for the effective mass. Like there are many different definitions. This is the one that I think has is the most established, so that's kind of why we've been using it.
I have a question, Duncan.
Yeah, go ahead, please.
So it seems to me that this is a very hard problem, right? Simulating a bunch of fermions, and you have all sorts of sign problems and all. So when you are trying to fit it with this feed-forward neural network, you mentioned number of hidden layers to be about 50. How does that number scale with the number of particles? Because the complexity must be somewhere hidden, right, in your neural network.
I see. Okay, so that's a good question. In general, the number of data points that you need would not depend on the range of particle numbers that you simulate, because as far as the network is concerned, this is just a number. Like the inputs to the network would be a number representing n, and so the learning of the network doesn't really depend on that too much. What happens is there are certain researchers who have done studies where they're building wave functions, for example, and because they're looking at the wave functions and trying to understand what details the networks are trying to capture, they can look at the actual internal hidden layers to see which, when things are activating and why. So there's this whole other study of studying why the networks, or what the networks are capturing, why they might perform really well, and we kind of treat it a little bit as a black box, but there are other researchers who do that. The data set size is what would typically determine the size of your model. The more data you have, the bigger your model can typically be. On the order of 1,000, it seems like on the order of 50 to 100 hidden units is sufficient for our problems. For other ones, like natural language processing, they have billions of parameters, and they're very, very complicated. So as this work kind of progresses and models get more complicated, I'm sure you'll see the size of networks explode.
Thanks.
Okay, let me maybe, so if there's no other questions at this point, and again, we have the session, a bit of time at the end of the session. So let's thank Nawar for a really clear talk. Thank you very much, Nawar. Let me stop the recording.